Great. Well, thanks so much for coming. We're going to do, today we're doing session on Gaussian processes. There's, we've got a nice small group, so we can take it nice and patiently. And, you know, you could interrupt me with questions if you have them. Okay, so my name's Niel Lawrence. I'm a professor of machine learning at Cambridge. And I've been working in Gaussian processes, I suppose, for maybe 20 years. Hopefully today I'll share some of the reasons why I enjoy working with them. Okay, so I'm going to share my slides. Do have a look on the, if you look in the chat, I've shared a couple of links. One is to this page here, which is the course notes. So you'll see here, there's a number of notes around, I don't know why they pulled to one side there. Let me just, oh, it's because the screen is so massive. There, anyway, that's smaller, sorry, easier to see. And as well as the notes being on an online page there, you'll find the same set of notes on a Colab. So if you've used Colab before, it's a way of getting a Jupyter notebook that's hosted by Google for you. And that notebook, when it loads, should show you the same type of notes, but also with code. And the code will allow you to try and recreate some of the examples. So this is all the introduction, so there's no code there. But for example, here, you'll see that there's some examples where you can run the code. So you can run the code yourself, and you can do that while we're talking, or you can also maybe try and do that later offline. Okay, great. So let me get rid of that. Go back to the class. Right, so Gaussian processes is our subject today, but I'm going to give you a bit of a motivation before we start. So first of all, this is a great book. It's available freely online, so you can find this book if you're interested in Gaussian processes, and you can read the book. It's a very helpful book in explaining a lot of the concepts. Here's another book I like for just talking about machine learning in the style that I'm presenting machine learning. So it's by Simon Rogers and Mark Girolami. Unfortunately, it's not available online, but it's about nearly 10 years old. So there's less about neural networks in here, but perhaps more about the type of philosophy and thinking I have for machine learning. Great. So let me start with a motivating example. So who are these three? So this is Ricardo Andrade Pacheco, who's in the middle, who was a PhD student of mine. He's Mexican. John Quinn, who is actually at Google AI Accra, but at the time we were doing this work, he was at Makerere University. And Martin Mubangizi, who's now a lead data scientist at UN Global Pulse in Kampala in Uganda, but at the time was a PhD student collaborating with Ricardo, my PhD student, on an example which I'd like to share with you, which is used Gaussian processes. So the idea is that here's a map of Uganda, and we've got all the different departments of Uganda, and each of these departments, they monitor disease. So if you have the district, sorry, it's not the department, it's a district, the Tororo district here, it is trying to monitor different diseases like malaria. I mean, this is before COVID-19, today, presumably COVID-19 as well, but typhoid, just whichever diseases are registered. And this data is available, but the data we get from these sites is directly from the health centers. So the health centers don't necessarily always have the skill to diagnose The disease, if it could be malaria, but it could be typhoid. They have very similar symptoms, as I'm sure many of you know. So it's difficult to determine between them without taking a blood sample and looking under the microscope. But many health centers don't have the capability to do that. However, in the Tororo district, there's also a Sentinel site. So Sentinel sites are sites in the district where they have a World Health Organization center that does a very careful diagnosis of disease. So in the Tororo district, in a place called Nagongera, there is a Sentinel site. I think there's 7 across the whole of Uganda. And if we look at the different traces of information we can get from the Sentinel site, you've got 3 traces. One at the top is the Sentinel site of all patients appearing at the Sentinel site. So this is all the people who report to the Sentinel site with some disease. Below that, you have the Sentinel site, those patients that were diagnosed with malaria. So this is a curve over time. And then below that still, we have another curve. Now this curve is the HMIS data. So the HMIS data is not the Sentinel site data. This is the data which is coming from the standard health centers. So the Sentinel site is the special site where they present the carefully curated data. And the HMIS site is one where you see the data for the entire district. And then we've also included some other things like rainfall and the temperature in the district, okay? Now, the task we were interested in is this Sentinel data here is very good quality. The HMIS data here is less good quality. But can we learn something about the relationship with this between these data to learn how well they're predicting the malaria patients? And then we can use that learning for all the other districts in Uganda where they don't have a Sentinel site to try and get better, more accurate predictions of malaria. And the idea for doing that is so that you can distribute nets or you can distribute medicine appropriately to deal with the disease in the district. Today, of course, we have the same challenge with COVID in many countries. But this is about 6 years ago we were doing this work. Okay, so here I'll give you a little example of whether this works. So this is a real plot from the Mubende, I'm not sure if I'm pronouncing that, Mubende district, where we have the ability to predict forward the data. And then below, this is a prediction where we're using all the additional information to try and form a better prediction. So here in the top plot, this is the standard data from Mubende. And you can see that as we try and predict forward what we think the malaria is, the red is test data. So the black is data we observe, and the red is data we don't observe. Now, of course, after we stop observing for some time, the prediction just goes to the average, okay? So this prediction is being done with a Gaussian process. And the idea in the project was to use a Gaussian process to inform the prediction by using this extra information from the Sentinel sites, from the weather stations, from the temperature. And this is an attempt to do that. Is this attempt good or not? I'm not really saying. Does anyone want to sort of say, I mean, maybe someone want to comment if people think this is a good attempt in the chat. Or we can even have you say something. Do you like the, which curve do you prefer, the top one or the bottom one? Come on, someone can answer. The bottom. Mastura prefers the bottom. The first. Excellent. The top, the first. The bottom, it's a good attempt. Yeah. It's hard to know, isn't it? I mean, I like the fact that you've all come up with different answers, because which is better, right? That goes right to the heart of machine learning. So the bottom one does more interpolation perhaps between the data, but there's this piece it's missing at the bottom. Actually, the bottom one is doing quite a bad job where there's training data in this black region there, because look at, these are error bars at 95% confidence intervals. At the top, they're nice and tight. At the bottom, they're very loose. So it sort of does a better job with perhaps with the mean function, but at the same time, it perhaps does a worse job with the variance. Anyway, Ricardo worked very, very hard with Martin as well. Let's just look at them again. They worked very, very hard on this project. So it was a project when I was at Sheffield, and we had Ricardo and Martin, who'll come up in a minute, worked as a team, very much as a team. So Martin did a lot of the, oh, it's gone too far. Okay, I'm just going to wait for that to calm down because it's spent too, it's received too many clicks and now it's confused. There we go. Is it going to stop there? This sometimes happens, and I don't know what causes it to happen when it happens. Let me just deal with this. Is it going to stop? Sorry about that. So Martin and I'll just say while it tries to sort itself out, Martin and Ricardo worked very hard on it. This idea of combining these plots that we can see in the image now. But in the end, I think we felt that we didn't do a good enough job. We felt that the result that we are seeing there, I mean, we also had a nice summer school. This is us all in Malaria doing a course a little bit like the one I'm doing in 2013. You can see in the middle, here's Ricardo, and Martin is here. I'm at the back here. John is at the back here as well. That's us in Malaria doing this course. But our feeling was that this job wasn't good enough. And as we investigated, Martin actually, Ricardo actually went to Kampala and worked more on the data. And we found that there were problems at the core of the data when we worked within the UN, which we could fix. And we in the end did a better job. And this is actually what Martin, what Ricardo came up with when he went back to Kampala after he'd finished his PhD. With that result, which we weren't actually that happy with, because some of the reasons you're saying, it's not clear it's better, and you have to be very careful to understand whether you're doing things that are better or not. And he built this instead, which is actually a much simpler thing. So what he found is the reason we weren't doing well is that those health centers, they were returning data every week or whatever the frequency of the data is, but not all the health centers were returning their data. So some health centers didn't return their data. So this is what's called a missing value. But when we saw the HMIS data for what the level of disease is, we didn't know that there were missing values. So we couldn't deal with these missing values, and it was confusing our entire system. So this is, first of all, a word of warning. You must be very, very close to the data. Because then, when Ricardo went back, and he started working with UN Global Pulse and could see the raw data. So before this, we were working in the university. Now where Martin works, but also Ricardo went, they looked at the raw data and they saw that there were all these missing data, and he had to deal with the missing data first. And then once he dealt with the missing data, rather than try and recreate his thesis work, he did something much simpler, and I think that in the end was more useful. What he said is, and this is for the Mubende district, I think, is he fitted the data, which you see on the left-hand plot here with the dots, with a Gaussian process model, which had two components. One that you see in red is a long-term trend, and one that you see in blue is a short-term trend. And what he's showing on the right-hand side here is something that we're going to visualize in the moment. He's showing on the y-axis, this is the curvature, sorry, the gradient of the blue curve. So if it's above 0 on the y-axis, then the gradient is positive. If it's below 0 on the y-axis, then the gradient is negative. Okay, so that's whether the rate of disease is going up or down. So when the dot's above the line here, like it is at the moment, the rate of disease is increasing. When it's below the line, the rate of the disease is decreasing. But he then also shows something else, because he's got the long-term trend in the red and the short-term trend in the blue. So on the x-axis, Ricardo is plotting whether the curve is below, that be the negative side, the long-term trend, or above the long-term trend. So what does this mean? What do we see on this plot? To explain this plot, there's 4 quadrants on this plot. This quadrant here, which is colored green, is that we are below the long-term trend for the disease, and the disease is decreasing. This quadrant here, which is colored yellow, is we are below the long-term trend for the disease, but the disease is increasing. So it's getting worse. So although it's in a good position, it's getting worse. So instead of coloring green, we color yellow. Red is when you're above the long-term trend. So you're now on the right-hand side of the axis, and things are getting worse. And orange is when you're above the long-term trend, but things are getting better. Okay, so that's the idea of this plot that Ricardo made. That's actually much simpler than the original work he set out to do. And then this is the result. He could then look at every district across the whole of Uganda. The reason you get these strange streaks going down is because that's Lake Victoria in the south. The districts go into Lake Victoria, right? And we could see at a glance where in the country there's a problem and where in the country, I mean, so this is fast forward, right? So this is on a weekly basis, right? So this is just going very quickly through, I think, 48 weeks or something like this. This plot is correlated with this work here, right? So this is over time, we're just moving forward. And you're very quickly able to visualize where there's a problem. So I guess the red is actually quite close to Kampala or down in southwest Uganda. But then in the east, you've got things are getting better. So a really nice visualization of the state of disease across the country in Uganda using very, very sort of simple, well, a simple idea, but based on top of a Gaussian process. So Gaussian processes are very useful models for this type of exercise. And that's kind of my motivation for why we're going to spend time studying them today. Let's just see if there are any questions. Let's pause and see, are we together? Do people see what I'm saying, that we could use these models to monitor disease? Let's pause. Any questions? We're a nice small group, so we can do questions. No questions? Just put a Q if you've got a question, and then you can even unmute yourself. Okay. No questions. Right. So I'm going to go a bit back to basics and ask you, what is machine learning? So I have an idea of what I think of as machine learning. In these examples, what we were trying to do is create a prediction of what the level of malaria was, given going to be in the future, in fact, given what we had, which was data from the HBIS data and maybe the Sentinel data. We're going to come to that, John Michael, what a Gaussian process is. Plus a model. And we combine them together to make a prediction, right? So in machine learning in general, this is mostly what's going on. It's not always like this, but it's often like this. So the data is a set of observations. And in this case, that was the malaria counts from the different districts. The model that we were using was a Gaussian process. And we're going to describe, that's what this session is about, is to describe that model. But in general, the model doesn't have to be a Gaussian process, but it does include your assumptions. So what you noticed the Gaussian process was saying is it thought that the data was smooth. It tried to smoothly interpolate between the different data points. So those assumptions can be based on previous experience or other data or beliefs about the regularities of the universe. So one that we keep seeing in the Gaussian process is that we believe that these curves were probably smooth. Now, it's very possible that a lot of people suddenly get malaria in a district at one time, but it's more likely that the numbers go up smoothly. And so we try and incorporate that assumption in our model. And the prediction, there's an action to be taken, a categorization or a quality score, or in our case, what's the level of malaria going to be in the future? Okay. So that's my idea of what machine learning is. Now, to combine that data with a model, we need a prediction function. So I would like to break down this sort of broad idea into the notion that we need to have a function that's going to produce our predictions. And that function is the thing that's going to include our beliefs about the way the universe works. So a mathematical function is what I mean here. And then typically, we also have to have an objective function. So the objective function is something that we use to better fit our prediction function to the data. Okay, so those are the two things we tend to use in machine learning: the prediction function and the objective function. And if you're fitting a neural network, the prediction function is a neural network. If you're fitting a linear model, the prediction function is a linear model. If you're fitting a Gaussian process, it's going to turn out to be a little bit different. Okay, so let's go back to basics and look at something that I like to sort of play with. This is an overdetermined system that we're going to look at. So here, the prediction function is very simple. It's just y is equal to mx plus c. It's a straight line. So quite often people study this in high school. So the idea is you have some input. So the input could be time, and the output y could be the amount of malaria. And the assumption is that over time, that in this case, the amount of malaria is going down in a straight line. So there's a gradient to that straight line. That gradient is given by m. Yeah. So because it's the sort of the difference, small difference in the straight line here divided by the movement in x. That's the gradient. And there's also an offset. So the offset is, often we think of the offset as where the straight line intersects the y-axis. Okay, so this is a great prediction function that we could use. And here's two data. Okay, so let's assume that we're observing the sort of malaria level at time 1, and it's 3 people have malaria. And then we observe the malaria level at time 3, and 1 person has malaria. That's brilliant. So now we can fit our straight line. Well, I mean, and then the straight line goes in there. Okay, great. But what happens if we get this third data point? So now instead, let's assume it's 3,000 people have malaria and 1,000 people have malaria. And now there's some time in between where 2,200 people had malaria. Okay, that's kind of problematic because now our straight line isn't fitting that point. So we can have a straight line that fits that point. Here's one that fits that point. Here's another that fits that point. And here's the third, the original straight line. So we've actually now have 3 different possible straight lines. Which should we choose? Does anyone have a choice, a preference? What should we do? Any suggestions? We've got 3 different straight lines here, right? Any thoughts? No thoughts. So this is a problem actually that goes a long way back. This is what's called an overdetermined system. So we've got 2 unknowns, m and c, and we've got 3 observations. That means we can't solve this system by a set of simultaneous equations anymore. So this is kind of the basis of where machine learning type work starts. And it started a long time ago. This is the problem. We've got point 1 was time was 1 and y was 3,000. Point 2 was time was 3 and y was 1,000. But then we had this third point where time was 2 and y was 2,500 people. Okay, so the problem is here, if we just have these two, then we can solve these equations for 2 unknowns. 2 equations, 2 unknowns. Here we've got 3 equations, 3 unknowns. We can't solve the equations anymore. So what do we do about that? Well, I'm going back to basics here, but this gentleman here is Pierre-Simon Laplace. And what Laplace said in this is in French, for those of you that are from a Francophone part of Western Africa. But here's the English. So what Laplace says is we ought to regard the present state of the universe as the effect of its anterior state and the cause of which is to follow. And then he says, given for an instance an intelligence that could comprehend the forces by which nature is animated, one that can submit these data to analysis, in the same formula, it would embrace the movements of the greatest bodies and those of the lightest atom. Okay, it's a long thing that he's saying here. And you'll see I unpick it in the notes. But basically he's saying, given for an instance that if we know the forces by which nature is animated, for me, that's the model, yeah? And then for the next line, he's saying the respective situation of the beings that compose it, that's the data. Sufficiently vast to submit this data to analysis, that's compute. Then we can have the same formula for movements of the greatest bodies of the universe and those of the smallest atom. That is prediction. Okay, so several of you have given answers to the sort of question I asked earlier. We could use a more complex model. Absolutely, Chirizurum, we could use a more complex model. We could pick the first line or use a more complex model. So what we're going to do is actually something that Laplace suggested instead. Because he's talking about modeling there. But then he later on, everyone calls that the deterministic universe, and Laplace is famous for it. The curve described by a simple molecule of air or vapor is regulated in a manner just as certain as the planetary orbits. The only difference between them is that which comes from our ignorance. Probability is relative in part to this ignorance, in part to our knowledge. We know that 3, blah, blah, blah. So what Laplace says is the following. When we look at this equation, we're missing something. So before we had y is equal to mx plus c, okay? But now what Laplace is saying, sorry, I suddenly went backwards. What Laplace is saying is that you're missing something when you have y equals mx plus c. You need to go beyond y equals mx plus c. There's something in your system. There's something in your system that's missing. So instead of a system like this with 3 components, with 3 equations, what Laplace says is there's part of that equation which we don't know about. And that part of the equation that we don't know about, I'm representing with epsilon here. Okay? So epsilon is what we can sometimes call a slack variable or noise. Now, let's look at the situation we had again. In the first case, we have this point, and what we're saying is that the observation 3 is equal to 1 times m plus c plus some corruption. In the next point, the observation 1 is equal to 3 times m plus c plus some corruption, but it's a different corruption. Notice I've written epsilon 1 and epsilon 2. So what we're basically saying here is that in each of these cases, there's some unknown thing going on, something that Laplace referred to as our ignorance. And the key thing that we're going to do is use probability to represent that unknown thing. Okay? So what Laplace actually said is that that missing thing is sampled from a distribution. And in our case, we'll think of that distribution as a Gaussian. Laplace didn't say that. Gauss was the first to say that. And that's in the notes. You can see the detail of that in the notes. So what we start thinking of as our model is a little bit more than just that function. And I want you to look at this equation here because I'm introducing a Gaussian. So what this is saying is that the probability distribution over yi, the malaria level we observe, given x, the time which we're making the measurement, is given by this formula here, where this is the formula of the Gaussian density. So what it's saying is it's equal to this normalization constant times the exponential of this form. And carefully look in here, because this f of xi, that's our function. So where you see that function appearing is normally where the mean of the Gaussian distribution appears. And what we're doing in this case is substituting the mean with f of x. So f of x being our prediction. So what we're saying is our observed value, y, is actually related to our function as it's the mean of the function, but then it's corrupted away from the mean as a Gaussian. People following that? So I don't know how, just put a y in the chat if you've seen the Gaussian distribution before. Or maybe put a, yeah, okay, good, Isaiah. Cool. Okay, because it's pretty tough if you haven't seen the Gaussian. Yeah, so the innovation here is normally in the Gaussian you have a mean, which is just a regular mean. But here our mean is a function of x. Okay? Good. So this gives us what we call a noisy function. So we're saying that what we actually observe is a function plus noise. And sometimes we will call this a stochastic process. Now, the Gaussian is a super useful distribution for this type of thing because there's two really important properties of the Gaussian distribution. If I have a Gaussian density, like I'm saying here, and this is just a normal draw from a Gaussian, forget here the mean isn't a function of time like it was in the previous example. If y is a draw from a Gaussian, then this formula is true. What this formula is saying is that if I add a load of y's together on the left, then they will also be sampled as a Gaussian. And the mean of that Gaussian will be the sum of the means of the original Gaussian. So this is just the sum of these. So we're just, the sum of the y's is drawn as a Gaussian whose mean is the sum of the means and whose variance is the sum of the variances. Very important property of a Gaussian distribution. Also, this other property is very important. So if I have a Gaussian variable that I scale, so if I've got something y and I multiply it by w, then if y is drawn from a Gaussian with mean mu and variance sigma squared, wy is drawn from a Gaussian with mean w mu and variance w squared sigma squared. Okay, so two very important properties. The first is not totally unique to Gaussians, the first property, but the second is almost unique, sorry, it's very common. It's very common that scaling a probability distribution leads to another distribution. But here we're only going to look at the Gaussian. Okay, I think we'll come back to the multivariate properties. I don't want to do them quite now. So that was an overdetermined system that I introduced, but I wanted to introduce something else. What about the case where I have just one observation? So instead of having two observations, I just have y1 and x1, and I need to determine m and c. So I can compute m if I know c, but where do I get c from? This is known as an underdetermined system. And let me give you an example. So here, what can I do if I want to fit, I've got one data point, and now I want to fit a straight line to that data point. Any suggestions? What can I do here? So before I struggled because I had too many and I introduced some uncertainty. Any ideas about what I can do in this case? I could make C0. Yeah, that's an interesting one. So if I made C0, that's from Chisholm, then I would have a line that would goes through here like this. So I would have a line that sorry, go back. I would have a line that would start down here and go through the spot like that. Yeah. Okay, so making C0 is interesting, but then I would need to know, you know, it's almost like if I do that, that's almost like pretending I have another observation. It's pretending that at X, the observation is 0. So that's an interesting idea. But of course, that's quite a strong assumption because now I think it's going to go flying up. So here's what I'm actually going to do. So there I've assumed C is minus something. But look, here's another line that's also consistent. Now, can you see what I'm doing in this case? How am I creating all these lines? Can anyone guess? I can consider this family of lines. Okay, how am I creating these lines, given that we've just talked about a Gaussian distribution? It's a bit like Chisholm said, but instead of making 0, what do you think I might be doing? Instead of making it 0, where did I get C from for those lines, do you think? Someone has to have a guess. Ha ha! Thank you, Lawrence. Excellent name as well. Draw random numbers. Yeah, so actually I'm drawing these randomly from the Gaussian. So just as before, we introduced the sort of the epsilon, Laplace introduced and said, okay, that's going to be from a Gaussian. Here, we're going to represent C by drawing random numbers from a Gaussian distribution. And that's the big leap in Bayesian inference. By the way, if you hear about anything about Bayesian inference, that's effectively what's going on. That you assume, if in the absence of knowledge, you assume that these variables are random. So the parameters are random. Okay. Okay, let's look a little bit at what that means by considering a Gaussian for height and weight. So what we're going to do is we're going to sample some random numbers from a Gaussian distribution of height. And what we're assuming here is that the mean is 1.7 meters and the variance is sort of 0.225 meters. So the square root of that would be the standard deviation. And weight, and we're assuming weights in kilograms. So the weight is 75 kilos with a variance of 36 kilos. So that's a standard deviation of 6 kilos. So if we look at such models, then when we sample from such Gaussians, this is what the Gaussian curve looks like. Oh, somehow I've lost my ability to sample from them. We can sample from these curves. And what we will see is a distribution of heights close to the mean, right? So that's the shape of the Gaussian. And I'm just doing that for the value of C. Now, let's have a look at what happens if I assume that I can sample height and weight independently. So what I do is I'm taking a sample from H, and you can see that sample here, and a sample from weight, and that sample is here, 65 kilos and around 1.7 meters, and I'm plotting it on my graph here. I'm plotting just above 65 kilos and about 1.7 meters, you can see on the x-axis. So I'm plotting the weight on the y-axis and the height on the x-axis. Now I can take multiple samples, and each of these samples, so here's another sample, corresponds to a weight here and a height here. Here the height came out almost exactly the same. It's right on the mean here. But the weight was very different. So the weight actually came out much higher, so that the points plotted up here. Here, I've got a weight which is between the previous two. So you can see it's landed here. The heights also come out almost exactly the same. That's the coincidence, right? Oh, here the height's a little bit different. And I can keep doing that adding basically samples. Now, what I've plotted on the left-hand plot is the joint distribution. And because I'm sampling these independently, this joint distribution is axis aligned. I can sample one, then the other, right? And in the Gaussian case, what I'm drawing is a contour. So this is like a hill. So you're seeing one contour of a hill at one standard deviation to represent what we think of as the probability density. So I'm plotting these plots on the X and Y axis, and I'm drawing one contour around the sort of density as it goes up. If I kept sampling many times, Dorcas, you're sort of, can you just mute yourself because there's some noise coming through? Thank you. What you can see is the density there actually would eventually go up. So you'd start seeing a lot of points falling close to the mean, which is here, the mean of the Gaussian, and some points falling further away, and you'd start to see a bump of density here and less points outside. So what the standard deviation means in these one-dimensional plot is 95% of all points should fall in one standard deviation. When you go into 2 dimensions, it doesn't quite mean that anymore, but that's the interpretation of 1 dimension. So that is the way we can get a joint distribution over 2 values. So we started by sampling C out of the Gaussian. But there's something wrong with it, because actually, if you're taller, you're often heavier, right? So because as you go up in height, you tend to go up in mass. And in fact, in reality, when people talk about height and weight, they tend to represent things of this body mass index, which reflects the fact that height and weights are correlated. So if we wanted to deal with this in the Gaussian density, we could introduce correlated Gaussians. So here we've drawn the same thing. Here, these Gaussians are the same, these marginal Gaussians, but now they're not independent. So look at the contour shape, right? So if you're taller, you're also more likely to be heavier, okay? So you can't sample from these independently anymore. In the past, we could just sample height and then we could sample weight because they were independent. Now we have to sample together both height and weight, or the height has to depend on the weight. So this is a key object that we're going to be using, which is called a multivariate Gaussian, and it's expressing correlation between the height and weight. Okay, so if I sample from this, what tends to happen is for taller values, they're also heavier. Okay, that's how we could express correlation through Gaussians, and you'll hear correlation talked about a lot even without Gaussian processes, so it's an important concept. Okay, next slide. Okay, so how is that coming about? Well, this is what happens in an independent Gaussian. So if you've got 2 independent random variables, the joint distribution is given by the product of those random variables. This little bit of math, it's in the notes. It just goes through the fact that you can kind of write these independent Gaussians in this way that treats them as matrices. And this is the way that we tend to write Gaussians in the multivariate sense. Okay, so I'm just introducing the multivariate Gaussian notation here. So now, in this case, instead of having 2 means, we have a vector of means, which I represent by mu, and we have a covariance matrix, which I represent by D. Now, in the independent case, that covariance matrix is just a 2 by 2, and it's diagonal values. And the vector of means is just a mu1 and a mu2. But when we made them interdependent, you can think of it as rotating that around. So if you look at these 2 previous plots we did, how you can view us introducing the dependence by this being a rotated version of this. Yeah, okay, you can see that by eye. And so what the maths is doing here is showing that if you do that mathematically, so you take this matrix object here and rotate it, what you get is, so here I'm rotating the space, I'm rotating y and I'm rotating mu, and then I can bring the r out, and what I get is a new object here where it looks the same as before. This is again the multivariate Gaussian, but now I've got this rotation matrix here that multiplies by D. And what we talk about that rotation matrix is the covariance matrix. So the covariance matrix is like a rotated version of that old matrix before, where the rotation R effectively gives you how much correlation you have going on. By the way, if you've ever done principal component analysis, you'll recognize this. Well, this is the principal component decomposition. So here's the inverse covariance, right? But if I just take that inverse away and take that inverse away, I have the covariance. And the principal component analysis is basically taking a covariance matrix and turning it into this decomposition. Very important analysis for any data scientist. So this is the form of the correlated multivariate Gaussian, that instead of having a sort of variance and a mean, we end up with a covariance. Okay, so I'm sort of introducing some concepts around Gaussians for those who aren't familiar, and the model itself. Okay. Any questions at that point? Because I'm going to shift gear again and I'm going to move into basis functions. There's quite a lot to fit in, so I apologize for moving a bit fast. Any questions? Just put a Q in the chat if you've got one, or you can type the question in. Okay.
Okay, thanks, Prof. Well, we don't have any question currently.
Cool.
So I think we can proceed.
Okay, so you said before, make the model more complex. Totally agree. And now I'm going to teach you the way of making models more complex. So what I'm going to introduce to you is basis functions. So before we had an X that was just a linear system, okay? And this is a really nice way of making models more complicated. It's very closely related as well to neural networks. So here, I'm introducing a new vector. Vector phi is made up of 3 elements. They effectively are functions of X, but the first element is a constant function of X. So phi of X is what we call a basis vector. And what it represents is the first element is 1, the second element is X, the third element is X squared. And what we now say is, instead of before where we had our, what we're going to do is we're going to combine, instead of before, we basically said we're going to combine, we're going to make our function a function of X plus C. Now we're going to introduce the ability to make that function also of X squared. So how do we do that? Well, first of all, something I'm going to use in the rest of the slides is a little bit of notation, and it's important notation. So let's just pause and look at it. So this is what we call a design matrix in statistics, and I think it's a good term. And what it represents is, if you've ever got a data set, it's you compute your basis functions. Each row is the computation of your basis functions for that data set. So your first data point, the first basis function is always constant. The second one here in the quadratic basis is linear before. So before, what we were doing to get our function is we were taking C times this column plus M times this column. And what we're going to give ourselves as an opportunity is to add this column multiplied by something as well. And that's how we're going to make things nonlinear. But the way we tend to notate this is we put each row, each data point in a separate row. Okay, so just to illustrate what this is, so what we're going to be doing is we're going to create functions. So here before, W0 was C, W1 was M, f of x, our function, was equal to C plus mx. But now we've changed the notation. We're using W, this vector, W0 plus W1x plus W2x squared. So we can draw what these basis functions look like across the real line. So before C, we were scaling this basis function plus C. This just moves us up and down. right? So if C is 0, like as we suggested before, then that basis function is there. And then we were taking this function here, phi of x. Now, multiplying this by m rotates this basis function, and that was giving us our straight line. In the quadratic case, we're going to add a third basis function. So the third basis function is just the quadratic form. And this gives us the opportunity to create new functions. So here, what I'm showing, again, is the function. And what I'm doing is I'm showing different new values of W0, W1, and W2. And what you see here in the white is the result of multiplying x, W0 by 1. So that's 0.255. So in this case, this function is the result of saying 0.255 times 1 plus minus, so in other words, plus minus, so minus 0.317x minus 0.859x squared. So what we've got is a gently sloping down line with some curvature, because we've taken this function, multiplied it by 0.255. We're taking this function, we've taken the negative of it, so it's a slight downward slope on the white line, and then we're adding in y, okay? And I can do that with a few different functions, and you can also play with this in the notes, right? So different values, and in this case, just like before, just like we did for C, I'm sampling these values from a Gaussian distribution, okay? So you can see how the sample of those values, but it's a trivariate Gaussian, but it's independent. Okay, so just like the original weights and heights, I'm taking a sample from each of these and multiplying it by the basis functions to give myself curves. So this is my model for functions. That I'm saying that f of x is given by the sum of these bases, but I'm sampling these parameters from the Gaussian density. Okay. So I'm choosing to do that with a quadratic function, but we can also do it with any basis function we like. So in this case, I've chosen a very particular type of basis function. This basis function here, I've got one of these, like I had before, the constant basis. You'll keep seeing that popping up. But here's another basis function I'm going to add. In this case, this basis function is this funny form. So this is the Heaviside step function. And what it's basically saying is, the form of this basis function is do nothing, but then at the negative of this value, have a gradient of 1, right? So I'm going to have a number of those bases, right? So I've got 4 of them. And why is this basis function important? Because this basis function is what's being used in neural networks. It's called the ReLU. So they'll call it an activation function, but we can also call it a basis function in statistics. The words are broadly the same in the context we'll be using them today. Now I can look at my little mini neural network and I can say, okay, what happens if I change the weights in this? So again, look, I'm getting different functions as I sample different weights, okay? So my trick here is that these functions are nonlinear, but they're nonlinear in X. What's very, very clever about them is look at W, right? They're linear in W. W never appears inside these brackets. It appears on the outside of these things. So this is called a linear model, not because it's linear in X, it's nonlinear in X because of these basis functions, but it's linear in W. It can basically be written as an inner product. So that's very nice, and we can use those models to fit nonlinear things. But the Gaussian process goes further than that. It's based on this basic idea, but in this case, you can get these basis functions to do nonlinear predictions, but you would need to choose a number and location of the basis functions. Gaussian processes are a very general framework. The basis function things we've just been seeing are a special case. And in the framework, you can consider models with infinite basis functions, which is pretty wild. So that's kind of what's very, very special about them, is that you can take this type of simple model, and instead of saying, I'm going to have 7 basis functions, you can just have infinite basis functions. Yeah, Chizurum, sorry, from before, yes, it was polynomial features. Yes, so this is we can extend this model. This is a polynomial fit. Yeah, absolutely. So we can actually add basis functions and have a higher order polynomial here. Okay, so that's basically the idea with Gaussian processes, is that instead of having a fixed number of basis functions, we do the same thing here, but we have infinite basis functions. Pretty wild. Okay, so just to sort of review what's going on in the fixed basis function model, as I said, those are called linear models. And in order to write them down conveniently, I'm going to use this little bit of notation. I've introduced the design matrix already, but I'm now saying the elements of this design matrix are given by the evaluation of the jth basis function. So each column is the evaluation of the jth basis function. And here there's h total basis functions. Sorry, this n should be, there's something wrong here. There should be a 1, yeah, there's something wrong in this row. I think the other rows are fine. Oh, maybe that should be an h. Yeah, that should just be an h. And this first thing should be a 2. There's an error in this row. The other rows are right. So we define the design matrix. And then this allows us to write down a matrix representation of a neural network. So a single layer neural network or a basis function model, because they're the same thing. So what we're saying now is the output of our neural network is equal to our f of x, which we can write as an inner product. So if you look back at these objects here, you can see that if you've got that basis vector, which is the form 1, and then this is the basis function, then this is the basis function, and this is the basis function, this f of x here is the vector w in a product with those basis functions, right? So that's what we're writing down. I go through this slower in the notes. That's what we're writing down here, the f of x. But then we're also doing the thing that Laplace introduced. We're corrupting with noise. So the observations are equal to f of x plus noise, but f of x is now this inner product between the parameters of our model, w, which in the linear case was m and c, but in the nonlinear case, we generally have more parameters than that, and our choice of basis function, our choice of number of basis function. But rather nicely, across our whole training set, if we define things as we did for this previous slide, we could write that model in this form, in linear algebraic form. If this is our design matrix, all observations, all predictions across our training data are given by our design matrix multiplied by the vector w plus some noise corruption epsilon. Now, what we said that Laplace introduced is that noise corruption is going to be sampled from a Gaussian distribution, right? So that's the sort of way that we dealt with the overdetermined system. That's the noise model. But what we're going to do as well, damn, I sort of thought I had that on here. We're also going to assume that W is sampled from a Gaussian distribution. So if we go back to multivariate Gaussian properties, so this is the key to a Gaussian process. So we had those univariate Gaussian properties, in order to get the Gaussian process, what you have to understand is that the multivariate Gaussian, those univariate properties have a consequence for the multivariate Gaussian. So remember we looked at before, we said, oh, well, the sum of Gaussian variables is going to be Gaussian, and the scaling of a Gaussian variables leads to Gaussian as well. Well, because linear algebra, matrix multiplication is just sum and scaling, you get this property as well, that if you do have a Gaussian of this form, and you sample, a formula of this form, where you've got linear algebra here, and you say that x is sampled from this Gaussian, and epsilon is sampled from this Gaussian, the multivariate Gaussian example tells you that y must also be Gaussian distributed, with the mean being equal to w times mu, where the original variable was x, and the original mean of that variable was mu. The new mean is W mu, and covariance given by WC transpose, WC W transpose. So before the covariance of X was C, the updated covariance is WC W transpose. So W on the mean multiplies one side, W on the covariance multiplies both sides. And because then we've added noise, a plus epsilon, which is the covariance of that noise. We added noise, which was zero mean. These formula mean that if we decide this is the case and we sample W from a Gaussian random variable, then Y, if W is Gaussian, because this is a linear relationship, Y must also be Gaussian. And that's the essence of a Gaussian process, that Y is going to be jointly Gaussian. But what happens is here, we assume that typically that W is independent, but Y turns out not to be independent. And that's because of this property. So it's a bit confusing because I flipped the W and X's here, but in the previous slide, we're sampling this value, the small one, which was W on the other slide. The small one sampled from a Gaussian with an independent covariance, so C is independent. But even if that's independent, Y is now correlated. Epsilon is also independent in the previous one, so this would be independent as well. So when you apply this formula, you find that even though you sampled X independently, because of the multiplication, Y is jointly correlated. And that's the essence of a Gaussian process. And this is what it looks like for the case where we sampled W independently. So we apply that rule to the previous formula. And if we're just assuming that we're sampling W from a univariate Gaussian, it turns out that Y is also sampled from a Gaussian with mean 0, because the mean of W is 0. So phi times 0 is 0, which would be the mean. But covariance, alpha phi transpose, because the covariance was given by W C transpose, and here W is phi, C is alpha I, and W transpose is phi. So the alpha I comes out the front, and you get phi transpose. Then you add the noise covariance, and the noise covariance capital sigma. In our case, we just define the noise as sigma squared, independent noise. So this is the covariance of the noise here. So that's just being added on at the end. So that is the distribution of Y. X is embedded here. It's inside phi. So don't forget that phi is sort of a function of X because we declared that design matrix. But we could also just look at the covariance itself and say, okay, this term contains something that is a covariance, and this covariance K is equal to alpha phi transpose plus sigma squared I. This is an n by n if n is the size of your data set. Okay, that's the essence of a Gaussian process. I know we've gone through that very quickly. We've gone from linear to quadratic to basis functions to Gaussian processes. But in the notes, it goes through it much, much slower. Okay, so the interesting point about that, though, is if you start looking at this object here, the kernel here, then you look at the elements of what this matrix must be, then they are a little function of each xi and xj. So we haven't gone through that in detail, but when you do this matrix product here, every element of this is a little function of the ith and jth data point. So where I is the row of k and j is the column of k. And this is that functional form in the case of the basis function model. Right, so I'm going to skip forward a little bit here and just look at another set of basis functions that we're going to use to build our Gaussian process. And again, the details are more in the notes, but this is known as a radial basis function model. And in this case, you've just got these sort of Gaussian bumps you're combining together. So just as before, we can combine the Gaussian bumps with different weights, okay? Now, what's nice about this radial basis function model is it converts to a very beautiful Gaussian process. So I think we've done that bit. We've effectively done that. That's all in the notes again. So the Gaussian processes we've talked about so far are what is known as degenerate. So those covariance matrices were of the form phi transpose. If you've played with linear algebra, then you'll recognize that as a matrix which has a particular rank. And the rank is actually at most h. So the number of basis functions is the largest the rank can be for that matrix. But what we're going to do in, so if you go for large n, you basically, it turns out that these matrices aren't full rank, and you end up with the determinant of them being equal to 0. These are known as degenerate Gaussian processes. And this does manifest itself in a particular way. The way it manifests itself is that they, earlier, I think there was this very good answer to the question, can we just make the model more complicated in order to deal with the additional data point? Now, the answer to that is yes, but how more complicated do you want? Every time we add basically that conforms to increasing h. But h is still fixed at some value. And that's what the degenerate nature of the Gaussian process means, is that there's some level of data that you'll see where the same problem will come up again. Now, in a Gaussian process, you do something different. You say, I'm going to go beyond that. And this is what Radford Niel did. So this is a picture of Radford Niel, who was the person that really introduced Gaussian processes into machine learning. He says, what would happen if you take h to be infinity? So if instead of having 3 Gaussian bumps, or 7 or 50, you just have infinite Gaussian bumps across the entire real line. And this is the page of his thesis where he starts suggesting it. So he's using slightly different notation to us, but the ideas that we've been talking about are what leads up to this in his PhD thesis. This is in 1994. And there's some maths for you to go through that. I'm not going to go through that with you today, but you can read about how that comes about, and you can see in the notes what happens. But I'm basically going to show you the result. The result is that you get a covariance function of this form. So you get a kernel, which is a function of, so here instead of xi and xj, I'm using x and x prime, which is a function of 2 values, but you no longer have that sum. Before there was a sum across the covariance function because of the inner product, the matrix inner product. But here that's gone because that's turned into an integral, and you just get this function here. And the nice thing is you can sample from the resulting process. So far what I've been showing you is the result of if I sample 3 different w's to give you a Gaussian process function. And as the result, I show you one function with 3 bumps. Now, what you can do as an exercise in the notes is sample directly from y. So instead of sampling w and then multiplying that by the basis functions, what this plot is showing you is the result of sampling directly from y. And this beautiful thing here is the result of doing what Radford Niel suggested and saying, imagine there's infinite basis functions. Okay, they have a certain width, but they appear going up and down everywhere. And I've sampled 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, I think 20 of these bases, these functions here. Each one sampled from the Gaussian process. And then the process of inference is, well, okay, here's very many, here's 1,000 of those functions. And the basic idea is if I have data, you can see here's 3 data points, and they only match some of those functions. So if I throw away all functions that they don't match, I'm just left with these out of the 1,000. And that is the process of doing prediction with a Gaussian process. So I start with that Gaussian process prior, which was the object I showed you earlier, which is the thing that I've sort of related to basis function models. I then combine that with data, in this case, 3 data points. And then I only consider data functions that are plausible under those 3 data points. I've thrown away all the others. Now, I've made that sound like a sampling process where I'm sort of throwing things away. But the beautiful thing about the Gaussian process is I can do that mathematically. So here is the result of just throwing away the other functions. But then what I'm showing you in yellow here, and with the error bars here, is the result of doing the maths and doing it analytically rather than just sampling in the way that I described. And that's what the Gaussian process allows us to do. So at the beginning, I was showing you a series of interpolations of data over time. And here I'm basically showing the result of combining those interpolations, the Gaussian process prior with the data to give us that type of interpolation. I've missed out lots of steps because it's difficult to fit everything into an hour and a half. In fact, we're already an hour and 12 minutes in, so we've only got sort of 15 minutes to cover. But it's a very, very different way of thinking about fitting functions, but it's got this beautiful characteristic that, look, where I have the data, I'm certain about where the function is. But outside the regimes of where there's data, I've got all this uncertainty represented by the error bars here, which is the shaded region. And then here's some samples from what those error bars would look like. So, you know, this function is going all the way up and coming down and going up again. That could definitely happen. That happens under the prior combined with this data. Okay, so this is what the form of that looks like. So this is the log likelihood, or this is the probability of the Gaussian process. So this is our model. We talked about data plus model. Here the data is entering as y, and it's coming into the covariance function as x, which we define. And then we've got some noise level sigma squared. But it all combines together to give us the probability of the observations we have given the input locations x. And that's how I tend to like to think of machine learning, is this little object on the left. Now, in practice, we often write this down in log form or negative log form, and we maximize it. That's known as the negative log likelihood. So that's what it looks like if you take it in log form. And in that case, you can see that instead of this exponential disappears and you just get this quadratic form. So this is a matrix quadratic form because there's a y here and a y here, and there's a matrix in between. So this is the multivariate version of a quadratic, okay? And a log determinant form. Okay, so I'm not going to go too much into the prediction stuff, but I'm just going to sort of take just one final thing. I'm going to just look at to try and give you a bit more intuition of the Gaussian process. So normally when you're doing a multivariate Gaussian, if you sample from it, you might expect those samples, you kind of probably expect them to be quite noisy. But what I'm showing you here is a single sample, one sample from a 25-dimensional Gaussian. Okay, so there's 25 points. It's a 25-dimensional Gaussian. It's multivariate, but it has a mean of 0. But it has a covariance that looks like this, where the white is 0 and the black is 1. Okay, so the Gaussian I'm sampling from has a covariance matrix that looks like this, but a mean of 1. So this means that any 2 points, if I take these points F1 and F2, which are sampled from the Gaussian, I've just plotted them against their index here. If I look at their covariance, they're very strongly correlated in this covariance. So it'd be a very tight rotation here that F1 and F2 should be very similar to another. Indeed, if I zoom in and I look at just the marginal distribution of these 2 data points here, what I see is the correlation is very, very high for these 2 data points here. So this model is saying that these 2 data points here are jointly correlated as a Gaussian. So let's look at the that joint density. So just as before, when we were looking at height and weight, I'm giving you the same plot here. So the same plot was what I'm showing you is F1, that was the first data point, and F2. And this is the covariance. And this is the single contour that we get. So the whole thing in the Gaussian process is that's the object you care about. And in a Gaussian process, when I make an observation, so here I've drawn a line, which is an observation of F1. So that purple line is my observation of F1. That gives me a conditional density of what F2 should be. So I'm drawing that as a bump here. So I've got a joint distribution of F1 and F2. And in the Gaussian process, if I condition on F1, I get a conditional distribution of what F2 should be given F1. Now, this little diagram here, what it's showing you is how learning works in a Gaussian process. Normally, in a neural network model, if I give it a data point F1, then I try and make a prediction from F2. I have to first of all do some optimization. Here, I don't do that optimization. I just condition my joint Gaussian over F1 and F2 described by this covariance to try and predict what my Gaussian should be over F2. That's what happens when two data points are close, but across that whole system, we also could have two data points that are far away. So here I'm doing the same thing, but in this case, I've got points F1 and F8. So these points have a much weaker correlation. So it's still a correlation, but it's 0.5 versus 0.986 it was before. And in this case, if I look at the contour of the Gaussian distribution, when I observe F1, and then I look at the conditional distribution of F2, it's much more diffuse, it's much wider. So I learn much less about F8 by observing F1 than I learned about F2 by observing F1. And indeed, if we go back to the plot, what we see is the point a distance 8 away is much less correlated than the points 2. So this whole function is being described by this correlation structure. Yes, underlying, it's an infinite set of basis functions, but the covariance function, which we get from that, describes what the relationship is between each of these data points. Okay, the final thing I wanted to just sort of show you is what happens if we then do optimization. Again, this is all in the notes. You can go through this very, very slowly in your own time. But when we want to combine this with a data fit, this is the form that we get. So there's some explanation of what's going on in this bit here. But we're going to skip that, but it's in the notes. Excuse me. And just go to, oh, I thought it was here. Oh, there we go. Okay, there we go. So what the last thing I'm going to show you is a data fit to it. Here's a data set, 1, 2, 3, 4, 5, 6 data points. And here's a data fit for a Gaussian process. Now, in this case, it's almost all noise. So here is the yellow is the mean function. It's very close to the data points. It's trying to go up to the data points, but far away from the data points, it's dropping back to 0. Now, this is because we've set the basis functions we're using in this case to be very, very, very narrow. So there's little RBF bumps. We've set the width of those to be too small. So it's too small really for this data set. But remember, I showed you that log likelihood term, negative log likelihood. Well, that's going to be plotted on the right here as I change the length scale. So look at the nice fits I start getting, okay? So I'm changing the length scale to one that is wider and wider, and that changes the quality of the fit. Okay? Now, if you look at the green curve on the right, I didn't go through the yellow and the cyan curves, but if you read the notes, you'll learn about them. But if you look at the green curve on the right, what you'll see is that it reaches a minimum error. And where's the minimum? There, it's going low and then it goes up again. So it's this curve here, the green curve. Watch that one, follow that one as I reduce. So it's going, it's the lowest there, it's higher before that. Okay, so let's stop where it's lowest. So that was this one. That's the fit it likes. And that's the beautiful thing about the Gaussian process. This isn't always true. If you put too many parameters in your covariance function, this becomes a problem. You can understand the right capacity control for your model. So you can use this log likelihood to select that length scale and get these beautiful fits of your function to the model. And everything I showed you at the beginning was being done using these techniques. So all that work to create then was there for allowing us to fit these models. Okay, there's lots more afterwards about different types of covariance functions and things you can read about. What I've tried to do in the hour and a half, and also showing you how to work different software, what I've tried to do in the hour and a half we've had is just go through the concepts that I want you to understand. And I know it's not easy to understand because we've gone through them quite quickly, but as you'll see, if I just scroll down through the notes, you'll see that here it's all gone through much slower, right? So you can focus on the bits that you find most useful in order to get a good understanding of how the Gaussian process fits being made. We've got, I think, 8 minutes before the end of the breakout session. But so I just want to use that to see if there are questions about Gaussian processes or anything I've said or how to run these things. So go ahead, I'll stop there. Questions? Surely Lawrence has a question for me because he's got his first name that I've got as a surname.
All right, thanks a lot, Prof. So if you have your question, you can just drop your question here so that Prof will attend to them before the time runs out. Thanks.
It's a lot of material to fit. By the way, you know, there's a lot of material online. How we can be, so Keras is probably not the right software to use for Gaussian processes. So there's some software listed at the end of the notes. One we use is called GPy, and there's another called, which is based on PyTorch, called Pyro. And those are the two I would be looking at. Can you use Gaussian processes in time series? Yes, they're very commonly used in time series. Is it okay? In fact, in the guise of Kalman filters, sometimes a Kalman filter is a particular type of Gaussian process. You could argue they're almost the most common approach for doing time series analysis. The problem with Gaussian processes in the general form I introduced is the computational complexity. So the operations you need to do what I've just done are cubic in the number of data points and quadratic in that's the computational complexity, and the storage requirements are quadratic in the number of data points. And that tends to be a disadvantage, but Kalman filters have a good way of getting around that for the specific case of time series. So Edigan says you joined the session late. Yeah, there we go. Thank you, Abel. All the material is there. And you can also find many, many lectures. So I've also included some links to other lectures I've given, which are longer. There's also if you want to check the Gaussian process summer school, which I'm just going to put it in the chat, then you'll find a lot of material there. The Gaussian process summer school kind of covers Gaussian processes over 3 days with a lot of lab classes and everything else. Other questions? We've got 5 minutes.
Thanks a lot, Prof. Really appreciate. I think there's no one asking any other question. Okay, there's a question.
We've got Chizurum is how effective is Gaussian noise for having small data? That's, yeah. So in practice, Chizurum, it's not so much small data, it's when you've got outliers that it can be a particular problem. In fact, there was a nice paper by Barbara Engelhardt's group recently on student T based noise. So you can relax the Gaussian noise assumption, but it just makes the maths a little bit harder, but people do it. For small data, I think it, yeah, is it? I mean, it's more like, it's not so much about the size of data, it's more what you think your real problem is. So certain situations, for example, where certain electrical signals, you sometimes get dropout on the signal, which is very non-Gaussian in its noise. And if you use a Gaussian noise for it, you don't get a very good result. So you do have to be very, very careful about that. So let me just, sorry, I accidentally sent this one. That's the link to the Gaussian process summer school pages that all the lectures are freely available, and the notebooks and everything else. Any other questions? Oh, that we're getting the current session will end in 3 minutes. Well, it's been very nice to have the chance to speak to you all. Yes. Yeah, what's the best way to do that? Maybe we also have a Reddit forum for our course. I'm wondering what the best way of doing that is. Let me it would be good to get a forum up. I wonder if Data Science Nigeria has something like that. I mean, what we do for my course online is we have a Reddit forum where people can ask questions, and then anyone can answer them, and of course, then they can be upvoted. So I think it would be maybe nice to set something like that up, so then everyone can see the same questions. What metric did Ricardo use to get the 4 severity groups? Right, sorry, I missed that question. Sorry, John Michael. Well, there's no metric there in some sense. It's just a decision, isn't it? It's saying, well, I want things to be below the average, and I want to know whether they're growing or decreasing. So those are the sort of 2 decisions he's made. He said, let's highlight when the curve is below the long-term trend, because that's good, right? So we can imagine in the COVID case, if COVID cases are less than they have been in the long term, that's a good thing. And let's also highlight whether the COVID cases are increasing or decreasing. So that was his idea. It's not so much a metric as a partitioning of the space. And then he's just given each of parts of those spaces the different colors. It's a really nice example, isn't it? I think it shows that a lot of data science is less about the fancy models. I mean, Gaussian processes are fancy models, but the important piece there is the visualization. I mean, if you did Elaine Insoeezy's course, she'll have spoken a lot about that. And it turns out the visualization is more important than the model. Yeah, you can catch me on Twitter, is it okay? That's probably the thing where I'm most responsive. Yeah, I'll have a think about trying to set up a little forum or something for specifically targeted at Gaussian processes for, I think particularly I'm really interested in African applications because you get these really interesting things like the thing we've just spoken about. And of course, I expect many of you are interested in those type of applications too. So that would be good, wouldn't it? Okay, I think we're just about to get thrown out.
Yes, thank you very much. Thank you very much, Prof. You only have 1 minute and we just want to appreciate you for your time. We thank you for thus far the class and the lecture. I appreciate everyone. If you want to reach out to Prof, you can reach out to him via Twitter, as he has mentioned. And the notebook and the session is, the link is in the chat and it will also be sent to you. Thank you very much, everyone. I think.
Thank you for coming. It was a great, and for inviting me. It was a great chance to give it.
Thanks a lot,
Jezerum. Ciao, ciao, everyone.
Yeah. So we can all move to the main room.